Hey, what's up guys? It's Pedro here from noobcoder.com. And in this tutorial, we are going to be talking about binary heaps in Python. So up until now, we've only been working with linear data structures, such as an array or a linked list. But now we're working with our first nonlinear data structure called a binary heap. So it's a tree data structure. So there are two types of binary heaps, a min-heap and a max-heap. Within this video, we'll be going over how to implement a min-heap using an array. So to get started, a binary heap must contain the following properties. The first being that a parent node must only have, at most, 2 children. The second property being that a binary heap must be a complete tree, meaning that it must be filled from left to right, and every level must be full, with the exception of the last level not needing to be full. So here's an example of a complete tree. You can see that all 3 levels are full. And here's another example of a complete tree. The first 2 levels are full, and the last one isn't full, but is filled from left to right. So this is also valid. This is not an example of a complete tree, since level 1 is not completely full before moving on to level 2. And once again, here's another example of a tree that isn't a complete tree. And this is not a complete tree because on level 2, we start filling our tree from the right. We should have started from the left and go right until the level is completed. Next, let's move on to the third property. The third property depends on whether or not you're implementing a min-heap or a max-heap. For a min-heap, every parent's key must be smaller than its children nodes. This ensures that the root node is always the smallest key within the heap. For a max-heap, the opposite is true. Every parent's key must be greater than its children nodes. This ensures that the root node is always the largest key within the heap. Now that we know the properties of a heap, let's talk about inserting data within the min-heap. So let's say that I want to insert 10, for example. Since our heap is empty, 10 becomes the root node. Now let's insert 20. So remember, we always fill our heap from the leftmost position. So 20 becomes the left child of 10. Once 20 is inserted, we must maintain the min-heap property, that the parent node must always be less than the child. This process is called heapifying our tree. In this case, we heapify up the tree, comparing the child node to the parent node, up until the root node. So since 20 is greater than 10, there's nothing for us to do, and our heap property remains intact. Inserting 5 into the heap, we insert at the leftmost position. So 5 becomes the right child of 10. But now our heap property is broken, since 5 is less than 10. To fix this, we just swap between the 2 nodes. This maintains the min-heap property that the parent node must always be less than the child. Inserting 30 into the heap, we insert at the leftmost position, so it becomes the left child of 20. Is 30 less than 20? It's not, so there's nothing left to be done. Inserting 15 now, we insert at the leftmost position, so it becomes the right child of 20. Is 15 less than 20? Yes, it is. So in order to maintain the heap property, we swap. We then keep going up the tree to make sure the heap property is maintained. So we check to see if 15 is less than 5. It's not, so there's nothing left to do. Inserting 3 into the heap, we insert at the leftmost position, so it becomes the left child of 10. Now it's time to heapify our tree. Is 3 less than 10? Yes, it is, so we swap. Is 3 less than 5? It is, so once again, we swap. Final example, inserting 0 into the heap, we insert at the leftmost position, so it becomes the right child of 5. Heapifying our tree, is 0 less than 5? Yes, it is, so we go ahead and swap. Is 0 less than 3? Yes, it is, so we swap here as well. So now, let's talk about how we could go about removing the smallest element within our heap. Since this is a min-heap, our root node is always guaranteed to hold the smallest element within the heap. So removing the smallest element is trivial. We just remove 0 from the heap. But now, our heap has an empty root, so we need something to replace it. So we replace it with the element at the end of our heap. So in this case, it's 5. Now, just like when we insert it into our heap, when we remove, we must make sure that our heap property remains intact, that every parent node is smaller than its child. So we heapify down until there are no more nodes. We check to see the smallest between the two children. So the right child is the only child smaller than 5, so we swap between the two. Now we check to see if 10 is less than 5. It's not, so there's nothing left to do. Removing the minimum element once again, so we go ahead and remove 3. Now it's time to get its replacement, so we take the last element within our heap, which is 10. Time to heapify down, so we check between the two children for the smallest element. Since 5 is the only child smaller than 10, we swap with 5. Last example, we go ahead and remove the minimum element. We then replace it with the last element within the heap. We compare 20 to its two children and take the smallest of the two, so we swap it with 10. So now let's talk about how we're going to represent a heap using an array. In order to do that, we're going to need a couple of formulas. To calculate the parent index of a given node, we take the floor of the index minus 1 divided by 2. To calculate the left child index of a given node, we take 2 times the index plus 1. And to calculate the right child index, we take 2 times the index plus 2. So given the following min-heap, let's go ahead and convert it into an array. First step, the root is always at index 0. So let's go ahead and store 1 at index 0. Next, let's calculate the root node's children. Using the left child formula, we use the root index, which is 0. So 2 times 0 plus 1 will give us the index of 1. So we store 2 at index 1. Calculating the right child, we get 2 times 0 plus 2 will give us the index of 2. So we store 3 at index 2. Next, let's go ahead and calculate the children of 2. 2 is at index 1. So calculating the left child, we get 2 times 1 plus 1, which will give us 3. So we stored 4 at index 3. Calculating the right child, we get 2 times 1 plus 2, which will give us 4. So we store 5 at index 4. Filling up the rest of the array, we should get the following. Now that our array is full, let's go ahead and test to see if the parent index formula works. So let's say I want to calculate the parent index of 4, for example. 4 is at index 3. So we get 3 minus 1, which gives us 2. 2 divided by 2 gives us 1. And if you take the floor of 1, you just get 1. So if we were to check index 1, you see that the formula does indeed work, and we get node 2 as the parent node. Alright, so from here, let's actually dive into the code. We'll create a class called Min-Heap, and within our Min-Heap, we'll define our init method. Our init method will have 2 params, our self param and the capacity. The capacity being the max number of elements that you want to store within the heap. First step, we're going to need a place to store this data. And as we went over previously, we're going to be implementing our heap using an array. Next, we need to set the capacity attribute to the capacity being passed in. And finally, we'll initialize our size attribute to 0. Size being the number of elements currently within our heap. Next, we're going to have a ton of helper methods. The first helper methods that we're going to be going over are going to help us calculate the parent and child indices. So we'll declare the getParentIndex method, which has an index param. The index param being the index of the node that you want to find the parent index of. So we'll just return index minus 1, floor division 2. Similarly, we're going to have a getLeftChildIndex and a getRightChildIndex, which will also have an index param, the index param being the index of the node you want to find the left or right child index of. So for our left child, we'll return 2 times the index plus 1, and for our right child, we'll return 2 times the index plus 2. Next, we'll have to define some more helper methods, this time checking to see whether or not a node has a parent, left child, or right child. So our hasParent method will return a boolean, and we'll have an index param. The index being the node that we want to know whether or not has a parent. So we'll return a boolean based on whether or not the parent index is greater than or equal to 0. If it is greater than or equal to 0, it has a parent. Otherwise, it means that the getParentIndex method is returning a negative number, which means there's no way this node can have a parent since we're using an array. Next, we'll have our hasLeftChild method and hasRightChild method, which have the same method signature. For our left child, we'll return whether or not the left child index is less than the size. If it is less than the size, that means that this node has a left child. If the left child index is greater than the size attribute, it can't have a child, since the size attribute is the number of elements within the heap. It is always at the last available free spot for insertion, which makes it impossible for the child index to be greater than that. Same thing can be said for the right child. We'll return whether or not the right child index is less than the size. If it is, that means this node has a right child. Moving on, we'll have helper methods to get the actual data from the parent, left child, and right child, and these methods are pretty self-explanatory. Next, we'll move on to the last two helper methods, our isFull method and our swap method. Our isFull method will be invoked whenever we go to insert within our heap to make sure that there is room before insertion. And this is a pretty simple test. We just return to see if the size is equal to the capacity. Moving on to the final helper method called swap, it's just your standard swap method. We take two indices to swap as parameters, and we just swap the data between these two indices. This method may be invoked whenever we need to reheapify our tree, when we go to add or remove an element. So now that our helper methods are out of the way, let's go ahead and talk about inserting into our heap. So our iterative insert method has a data param, the data that we want to insert within our heap. First, we check to see if we have space to insert within our heap. If our heap is full, we'll just go ahead and throw an error. Next, we'll go ahead and insert this data at the last available position within our heap. Once we've successfully inserted within the heap, let's go ahead and increment the size. And finally, once that's been done, we need to make sure that the data was stored in the right position. So we need to invoke our HeapifyUp method. Taking a look at our iterative HeapifyUp method, we start at the freshly inserted element, which can be found at size -1. Once we have our starting point, we need to keep walking up the tree, heapifying it. So we'll use a while loop to keep walking up the tree. We want to keep going as long as we have a parent node, and as long as the parent element is greater than the node element we're currently at. If it is, we need to swap between these two indices to maintain the Min-Heap property that the parent must be less than the child. After we swap, we continue advancing up the tree. Alright, so enough talk. Let's go ahead and see this method in action. So we invoke our insert method, inserting 10 into the heap. So first, we check to see if our heap is full. It's not, so we move along. We then save the data at the last available position. So our size attribute is at 0, so that's where we'll be saving. Once we do that, we then go ahead and increment the size, since we successfully inserted within the heap. And then finally, we invoke our HeapifyUp method. Within our HeapifyUp method, we get the index of the last element within our heap. We then go ahead and execute our while loop and check to see if this node has a parent. It doesn't, so this kicks us out of the loop. Executing our insert method for the second time, this time inserting 20. We first check to see if the heap is full. It's not, so we go ahead and store 20 within the last available position within the heap. We then go ahead and increment the size, since we successfully inserted within the heap. Now all that's left to do is to make sure 20 was inserted in the right spot by invoking our HeapifyUp method. Within our HeapifyUp method, we first get the index of the last element that we just inserted. Executing our while loop, we then check to see if this node has a parent, which it does. We then compare to see if the parent is greater than the child. It's not, so we get kicked out of the while loop. Executing our insert method once again, this time passing in 5 as an argument. First, we check to see if the heap is full. It's not, so we go ahead and save 5 within the last position within our heap. We then go ahead and increment the size, since we successfully added to the heap. Now it's time to test to see if 5 was inserted in the correct position by invoking our HeapifyUp method. First, we get the index of the last element we just inserted. Next, let's execute our while loop. Does this node have a parent? Yes, it does. Is the parent greater than its child? Yes. So we go ahead and swap the data between the two nodes. We then go ahead and advance up the tree. Executing our while loop once again. Does this node have a parent? It doesn't. So there's nothing left to do, so we get kicked out of the loop. Alright, so from here, we pretty much know how the iterative version of our HeapifyUp method works. But trees are naturally recursive. So let's go ahead with the recursive implementation. So first, we have to make a minor edit within our insert method. When we go to invoke our HeapifyUp method, we have to pass the index of the last element we just inserted. Taking a look at our HeapifyUp method, we do have to change the method signature since we're passing in an argument. So now we have an index param. Since we're getting out index being passed in as an argument, we no longer need to calculate the index within our HeapifyUp method. Next, we still need to go up the tree so we can actually steal the conditions that we used within our while loop with the iterative version and just use it as an if statement. So if this condition isn't true, there's no need to continue. But if it is true, we swap the data between the two nodes, so the node that we're currently at and the parent node, and then we recursively climb the tree by passing in the parent index to our HeapifyUp method. Alright, so from here, let's go over our recursive implementation. So we'll have our call stack just to trace the main methods. So we invoke our insert method once again, this time passing in 8. So let's push this on top of the stack. We then check to see if the heap is full. It's not, so we go ahead and store 8 within the last position within the heap. We then go ahead and increment the size after insertion. And finally, we go ahead and invoke our HeapifyUp method, this time passing in the index of the last element within the heap, which should be 3. So we push this into the stack as well. Within our HeapifyUp method, we check to see if the node we're currently at has a parent. It does, and is this parent greater than the child? It is. So we go ahead and execute the if statement. We swap the data between the two indices, and then we recursively call our HeapifyUp method, this time passing in 1. So now this gets pushed onto the stack. Once again, we check to see if the node we're currently at has a parent. It's true. Is the parent greater than the node we're currently at? It's not. So this if statement doesn't get executed. So we're done with this HeapifyUp method. So we pop this off the stack. We get returned to the previous HeapifyUp method, which is now also done executing. So we pop this off the stack as well. We then get returned to the insert method, which is now also done executing. So we pop this off the stack as well. Alright, so let's go ahead and give one more example with the recursive implementation. So let's go ahead and invoke our insert method, this time passing in 0 as an argument. So let's push this on top of the stack. So is the heap full? It's not, so let's go ahead and store 0 within the last position within the heap. We then go ahead and increment the size since we successfully added to the heap, and then we invoke our HeapifyUp method, passing in the index of the last element we inserted, which is 4. So we can push this on top of the stack. Next, we check to see if this node has a parent. It does. Is the parent greater than the node we're currently at? It is. So we could go ahead and swap between the two indices. We then go ahead and recursively call our HeapifyUp method, this time passing in 1. So let's go ahead and put that on top of the stack. Executing our HeapifyUp method once again. Does the node we're currently at have a parent? Yes, it does. And is the parent greater than the node we're currently at? Yes, it is. So we go ahead and swap between the two indices. We then go ahead and recursively call our HeapifyUp method once again, this time passing in 0. So we push this on top of the stack. Executing our HeapifyUp method once more. Does the node we're currently at have a parent? It doesn't, so we don't execute the if statement, and is done executing this HeapifyUp method. So we go ahead and pop this off the stack. We then get returned to the previous HeapifyUp method, which has also finished executing, so we could pop this off the stack as well. And finally, we get returned to the initial HeapifyUp method, which we can say has also finished executing, so this gets popped off the stack, which we then get returned to the insert method, which has now also finished executing, so this gets popped off the stack as well. Alright, so now that we talked about the iterative and recursive implementation of the insert method, let's go ahead and talk about our RemoveMin method. So our iterative RemoveMin method, and it removes and returns the min element. First step, we check to see if our heap is empty. If it is, let's go ahead and throw an error. Next, if our heap isn't empty, let's go ahead and save what's on top of the heap. We then go ahead and remove and replace the root element with the last element within the heap. Now that we successfully removed the root element, let's go ahead and decrement the size. Now it's time to make sure the element that we inserted at the root is in the right position. So let's go ahead and invoke our HeapifyDown method. And once that's done, let's go ahead and return the data. Taking a look at our iterative HeapifyDown method, first we need to start at the root node. So that's at index 0. We then need to go down the tree, so we'll use a while loop, and we want to keep going as long as we have a left child. Now the reason we only check for the left child is because a heap must be a complete tree, so it must be filled from left to right, so we only need to check the left child, since if it doesn't have a left child, there's no possible way for it to have a right child. Next, we need to find out the smallest between the two children. So we initialize the smallest to the left child. We then check to see if there is a right child, and if the right child is smaller than the left, we then make that the new smallest. We then go ahead and check to see if the node we're currently at is already less than the smallest of its two children. If this is true, that means that all our elements within the heap are in the right position, and there's nothing for us to do. So we break out of the loop. If that isn't the case, that means we need to swap between the parent and the child. And afterwards, we need to continue moving down the heap. Alright, so from here, let's go ahead and see our RemoveMin method in action. So given the following heap, let's go ahead and invoke our RemoveMin method. First step, we check to see if our heap is empty. It's not, so we go ahead and save the data at our root node. We then go ahead and replace the root node with the last node within the heap, which in our case is 30. We then go ahead and decrement the size since we successfully removed a node from the heap. Now it's time to make sure that the data that was inserted within the root node was inserted in the right position. So we go ahead and invoke our HeapifyDown method. So from here, we need to traverse down the tree. So we start at index 0, which is our root. We then start to go down our tree, so let's execute our while loop. First, we go ahead and initialize our small child index to the left child. We then go ahead and see if the right child is smaller than the left. It's not in this case, so we know the smallest child between the two is the left one. So now from here, we can go ahead and check to see if the current node we're at is smaller than the left child. So is 30 less than 5? No, it's not. So we go ahead and swap between the two. We then go ahead and advance further down the tree. So do we still have a left child? Yes, we do. So we execute our while loop once again. We initialize the smallest to the left child. So is the right child smaller than the left child? In this case, it is. So we set smallest to the right child. Next, we test to see if the node we're currently at is smaller than the smallest child. In this case, this fails. So we go ahead and swap between the two indices. And then we go down the tree. Executing our while loop once more. Does the node we're currently at have a left child? It doesn't, so we're done executing our HeapifyDown method. So we go ahead and get returned to our RemoveMin method, where we now go ahead and return the data that was removed from the heap. Giving one more example of our iterative RemoveMin method, first we check to see if our heap is empty. It's not, so we go ahead and save the data at our root node. We then go ahead and replace the root node with the last node within the heap. And then from here, we can go ahead and decrement the size, since we successfully removed a node from our heap. Now, it's time to put our newly inserted root element in the right position. So let's go ahead and invoke our HeapifyDown method. From here, we have to traverse down the tree. So we start at the root node, which starts at index 0. and we want to keep going as long as we have a left child. So do we have a left child? Yes, we do. So we go ahead and initialize smallest to the left child. We then go ahead and check to see if the right child is smaller than the left. It's not, so we go ahead and check to see if the node we're currently at is smaller than its smallest child. It's not, so we go ahead and swap between these two indices, and then we continue advancing down the tree. Executing our while loop once more, do we still have a left child? Yes, we do. So we continue executing our loop. We go ahead and initialize smallest to the left child. We then compare the left child to the right to see who's smaller. Since the left child is smaller, we get kicked out of the if statement. We then go ahead and check to see if the node we're currently at is smaller than the smallest of its two children. In this case, the parent is smaller, so there's nothing left to be done, so we break out of our while loop. We then get returned to our RemoveMin method, where all we have to do from here is go ahead and return the data from the removed node. Alright, so now that that is out of the way, let's go ahead and talk about the recursive implementation. So bringing up our old RemoveMin method, there is only one line that we have to change, and that is when we go to invoke our HeapifyDown method. We need to pass in 0 as an argument, so we're always starting at the root index when we go to HeapifyDown. Alright, so now from here, let's take a look at our HeapifyDown method. First, we have to modify the method signature to accept an index param. So now we have to find the smallest element between the parent and its two children. So for now, we'll initialize the smallest to the parent. Next, we'll need to check to see if we have a left child, and if the left child is smaller than the parent. If it is, then we just set the smallest to the left child. From here, we now check to see if there is a right child, and if the right child is smaller than whoever the smallest is. So that could be the parent or the left child. So if this is true, we set the smallest to the right child. Now that we know who the smallest is, we now check to see if the smallest is not equal to index. And remember, index being the current node that we're at. So if this is true, this basically means that either the left or right child is smaller than the node we're currently at. So we can go ahead and swap between the two indices to maintain our heap property. From here, all that's left to do is continue going down our tree. So we go ahead and recursively call our HeapifyDown method, passing in the smallest index. So if this if statement doesn't execute, that means that there are no children smaller than the node we're currently at, so we're done heapifying. Alright, so from here, let's actually give a couple examples of our recursive implementation. So since this is recursive, we'll have a call stack, which will keep track of the main method calls. So given the following heap, let's go ahead and invoke our RemoveMin method. So let's put this on top of the stack. First, we check to see if our heap is empty. It's not, so we go ahead and save the data at our root node. We then go ahead and remove the data at our root node by replacing it with the data from the last node within our heap. We then go ahead and decrement the size since we successfully removed a node within our heap. Next, let's go ahead and invoke our HeapifyDown method, passing in 0 as an argument. So let's go ahead and push this on top of the stack. Within our HeapifyDown method, we initialize smallest to the node we're currently at. So does the node we're currently at have a left child? Yes, it does. Is the left child smaller than it? Yes, so we could go ahead and set smallest to the left child. So now we check to see if the node we're currently at has a right child. It does. Is the right child smaller than the current smallest node? It's not, so this if statement doesn't get executed. We now check to see if smallest does not equal to the current node we're at. It's not, so we go ahead and swap the data between the two indices, and then we continue traversing down the heap by recursively invoking our HeapifyDown method. So let's go ahead and push this on top of the stack. So executing our HeapifyDown method once again, first initialize smallest to the node we're currently at. We then check to see if we have a left child. We do. Is the left child smaller than the node we're currently at? Yes, it is. So we set smallest to the left child. We now check to see if we have a right child. We do. Is the right child smaller than our current smallest? Yes, it is. So we set our smallest to the right child. Now that we got our smallest, let's go ahead and execute our last if statement. So smallest does not equal index, so we could go ahead and swap. We then go ahead and continue traversing down the tree by recursively invoking our HeapifyDown method. So let's go ahead and push this on top of the stack. Executing our HeapifyDown method once more, we initialize smallest to the node we're currently at. Does this node have a left child? No, it doesn't. Does this node have a right child? No, it doesn't. Is smallest not equal to index? This fails. So there's nothing left to do. So this HeapifyDown method is done executing. So we could pop this off the stack. We then get returned to the previous HeapifyDown method, which has now also finished executing. So we could pop this off the stack as well, which we then get returned to the previous HeapifyDown method, which has now also finished executing. So this gets popped off the stack as well. We then get returned to our RemoveMin method, where we continue executing our code. So we go ahead and return the data. And since this has also finished executing, we could pop this off the stack as well. Giving one more example, let's go ahead and execute our RemoveMin method, pushing it on top of the stack. First, we check to see if the heap is empty. It's not, so we go ahead and store the data at our root node. We then replace it with the data from the last node within our heap. We then go ahead and decrement the size, since we successfully removed the node from our heap. And then finally, it's time to make sure that the data that was inserted in the root is in the right position. So let's go ahead and invoke our HeapifyDown method, pushing this on top of the stack. So first, we initialize the root node to the smallest. We then check to see if we have a left child. We do. Is the left child smaller than the root node? Yes, it is. So we go ahead and set the smallest to the left child. We then check to see if we have a right child. We do. Is the right child smaller than the smallest? It's not. So we get kicked out of this if statement. We now check to see if smallest does not equal the current node. It doesn't. So we go ahead and swap between the two indices. We then continue going down the tree, so we could recursively invoke our HeapifyDown method. So let's go ahead and push this on top of the stack. Executing our HeapifyDown method once more, we initialize the current node as the smallest. We then check to see if we have a left child. We do. Is the left child smaller than the current? It's not. So now let's go ahead and check the right side. So do we have a right child? Yes, we do. Is the right child smaller than the current node? It's not, so this condition fails as well. Next, we check to see if smallest does not equal the current node that we're at. This also fails. So now we're done executing this HeapifyDown method. Let's go ahead and pop it off the stack. We then get returned to the previous HeapifyDown method, which has now also finished executing. So we could pop this off the stack as well. We then get returned to the RemoveMin method and continue where we left off. So all we have to do is go ahead and return the data. And now, since our RemoveMin method has also finished executing, we could pop this off the stack as well. So that is pretty much all I wanted to cover within this tutorial, and I'll see you guys in the next one.